The Hack CPU has a deceptively simple design. It is comprised of the ALU, which performs all arithmetic and logic calculations, a program counter, and 3 registers, the A register, D register, and M register, which outputs the currently selected memory register. It takes a 16-bit instruction input, which is split into a variety of logic gates and buses to send control bits to the ALU and multiplexers to determine the computation to process and which registers to send to the ALU. The Hack CPU chip has 3 inputs in total. The first is IN-M, which is a 16-bit input containing the contents of RAM A, meaning that the RAM register to be loaded depends on the contents of the A register. The second is instruction. This is a 16-bit instruction which comes from the ROM. Exactly which instruction is to be executed is specified by the program counter. The last input of the CPU is reset, a 1-bit input. If reset is equal to 1, the A register, D register, and the program counter are all reset. Otherwise, if reset is equal to 0, the CPU continues executing the current program. It also has 4 outputs. Out-M, a 16-bit output that is linked to the data memory to write data from the CPU to the current register, RAM A. Write-M is a 1-bit output that carries a load to specify whether RAM A should accept an input or continue to output its current contents. Address is a 15-bit input that carries the address of the RAM to be output by Out-M. PC is a 15-bit output that carries the ROM address of the next instruction. It is output by the program counter. The Out-M and Write-M outputs are combinational, meaning that they instantaneously output their values according to the current instruction. The address and PC outputs, meanwhile, are clocked and take a clock cycle to commit to the new values specified by an instruction. The CPU is made up of 23 parts, not counting the parts that make up the components that the CPU is implemented with. The majority of these are logic gates used to translate the given instructions so that the correct information goes to the intended input and to control loads for the various registers. We first consider the instruction input. Bit 15 of the instruction input is routed to a NOT gate, which outputs A instruction. This is routed to another NOT gate, which takes A instruction and outputs C instruction. The result of this is that bit 15 is inverted. If bit 15 is 0, it becomes 1, and A instruction carries a positive output. As it flows into the second NOT gate, it is inverted again, so that if bit 15 is 1, A instruction carries 0 and C instruction carries 1, and vice versa. An AND gate combines C instruction and bit 5, D1, from the instruction input. If both are 1, then 1 is output to ALU to A, which is fed into cell in the following MUX16. This MUX16 takes the 16-bit instruction input and also the 16-bit output of the ALU. The input for cell comes from the previous AND gate and determines whether to pass on the instruction input or the ALU output to the A register. In effect, if an instruction is a C instruction, bit 15 is 1, and bit 5 is also 1, this is D1 in the instruction, it will route the output of the ALU to A reg in, the input of the A register. If either C instruction or instruction 5 is 0, the instruction input will be routed to the A register instead. The next chip is an OR gate. It takes A instruction and ALU to A as inputs. If either input is 1, it sends a load to the A register via load A. This means the A register will accept an input and replace its current value. The A register takes A reg in from the previous MUX16 as an input, and the previous load A as a load. It outputs a 16-bit output to A out. A out is then fed into a MUX16 along with IN-M from the CPU's input. Instruction bit 12 is fed into cell to determine if the output of the A register or the output of the M register is to be output to AM out. An AND gate combines a C instruction and bit 4, D2, from the instruction input. If both are 1, then 1 is output to load D, which is fed into load in the D register. This is because D2 in the instruction indicates that D will be written to in a C instruction. The D register takes ALU out, the output of the ALU, as an input, and load D from the previous AND gate as load. It outputs to D out. If a C instruction with D2 as 1 has not been executed, D register will continue to output its previous contents. The next chip is the ALU. It takes D out as an input and AM out, either the output of the A register or the output of the M register, in M, depending on the previous MUX16 as inputs. It takes instructions bits 6 to 11, C1 to 6 of the instruction, as control bits, which are routed to ZX, bit 11/C1, NX, bit 10/C2, ZY, bit 9/C3, NY, bit 8/C4, F, bit 7/C5, and No, bit 6/C6. Its outputs are ALU out, which is routed to a previous MUX16, deregister, and also a later OR16 gate. ZR out and NG out, the last two, will be used to calculate whether to perform jumps later on. The next two chips are OR16 chips that are both used to route outputs. In both gates, the A input is wired to the ground, resulting in false, so the output will always be the B input unless the input happens to be all zeros, in which case, both inputs are identical and the output will be the same regardless. The first gate routes bits 0 to 14 of A out, the A register's output, to address M. This is for when the A register will be used to store an address. Bit 15 is not used for addresses, as it is used to signify whether an instruction is an A instruction or a C instruction, so it is not routed anywhere. The second OR16 directly routes ALU out to out M with no modifications. The next chip is an AND gate. It takes C instruction and instruction 3, D3, as inputs. If both are 1, it sends a load to write M. This will be routed to the data memory module and will signify to RAM A, the selected memory address, to accept an input and overwrite its contents. If either C instruction or instruction 3 are 0, no load will be sent and the memory will not be overwritten. The next gates are all related to whether to perform a jump or not. For the next AND gate, if ZR out from the ALU is 1 and instruction 1, J2 are positive, it outputs 1 to JEQ. The next AND gate will output 1 to JLT if NG out from the ALU is 1 and instruction 2, J1 are positive. This is followed by an OR gate that combines the inputs of ZR out and NG out to output 1 on 0 or neg if either input is 1. A NOT gate inverts 0 or neg to output 1 on the positive bus if neither ZR out nor NG out are 1, meaning the input to the ALU must be positive in this case. The positive bus and instruction 0, J3, are combined in an AND chip, which outputs 1 to the JGT bus if both inputs are 1. The next two OR gates combine inputs. The first combines JEQ and JLT so that if either of them are positive, JLE is positive. Then, JLE and JGT are combined and output 1 to the jump to A bus if either are positive. The end result is that if any one of the JEQ, JLT, JLE, or JGT are positive, jump to A will also be positive. The next AND gate checks that both jump to A is positive and that the current instruction is a C instruction. While any of the previous jump checks might be fulfilled by chance by an A instruction, they are not relevant if the current instruction is not a C instruction, so the gate filters this incorrect input out. We then have a NOT gate to convert PC load into PC increment. If we're not performing a jump instruction, we want to increment the program counter, so a PC load of 0 gets converted to PC inc of 1, incrementing the program counter by 1. The final chip is a program counter itself. It takes A out, the output of A register, as an input. If PC load is 1, it will output A out as the next ROM address to load, performing a jump. Otherwise, PC inc will be 1, and the address will be incremented by 1 to progress to the next instruction. The program counter also takes a reset input that will reset the instructions to 0, restarting the program.